This is Pre-Calculus A, Unit 5 on exponential, logarithmic, and piecewise functions. Lesson 3, we're going to do some graphing of logarithmic functions. Understanding the graph of a logarithmic function goes hand in hand with understanding the graph of an exponential function. So let's go ahead and start with that. So let's graph two functions, actually not log yet. I'm going to graph y equals, or f of x equals, 2 to the x, and then I'm going to graph y equals log base 2 of x, and we're going to compare the two. All right, so let's just think it through in terms of x values. So we're going to put in x values and we're going to get out y values. So here's my x-axis, my y-axis, okay, x-axis and y-axis, okay. All right, and let's graph y equals 2 to the x. So y equals 2 to the 0 is 1. Anything to the 0 power is 1. Y equals 2 to the 1 is 2. Y equals 2 squared is 4. Y equals 2 cubed is 8. And that's about as far as we're going to get. But let's go the other direction. Y equals 2 to the negative 1 is 1/2. Y equals 2 to the negative 2 is 1/4. Y equals 2 to the negative 3rd is 1/8. Y equals 2 to the negative 4th is 1/16. So we can hopefully see that this is tending off to 0 asymptotically. And we get the familiar exponential graph of a ski jump or an airplane taking off. It gets steeper the further you go to the right, and the steeper it gets. The further you go to the left, the flatter it gets. Okay? So y equals 2 to the x. All right, now let's graph y equals log base 2 to the of x. So think of 1 for example. 2 to what power, 2 to what power is 1? The answer is 0. 2 to the 0 power is 1. Okay? Go to 2. 2 to what power is 2? 2 to the first power is 2. Okay, now I can't say 2 to what power is 3 very easily, but I could say 2 to what power is 4? 2 to the second power is 4. I can't say 2 to what power is 5 very easily. It's not a very nice number. But I could say 2 to the power of 8, or 2 to what power is 8, and 2 to the third power is 8. Okay? Same thing down here. 2 to what power is 1/2? Well, 2 to the negative 1 power is 1/2. 2 to the what power is 1/4? Well, 2 to the negative 2 power is 1/4. 2 to the what power is 1/8? 2 to the negative third power is 1/8. 2 to the negative fourth power is 1/16, and so on. Okay, and remember what we learned about inverse functions. Inverse functions, y equals log base 2 of x. Inverse functions are symmetric about the diagonal line y equals x. Okay, y equals x. So take a look at this here. If I draw the diagonal, dia meaning through, diagonal, okay, then we can see the blue is a reflection across the orange. And so that reflection property, that switching of x and y that happens in logarithms is very important to note. The log function is the inverse of the exponential function. Okay. Another couple of things that bear mentioning. The exponential function has a horizontal asymptote at the x-axis. The logarithmic function has a vertical asymptote at the y-axis. You cannot take the log of a negative a negative number, because you cannot find a positive base raised to any power that will give a negative result. Okay? Remember, the answer to a log is an exponent. Okay? And so it behaves much like this. Okay? The other thing I want to point out, and I'm going to pull up Desmos for this, because I don't want to take too terribly long recalculating it. But I want to compare y equals 2 to the x and y equals 3 to the x. Okay, so let's pull up Desmos. Desmos, not Desleast. Okay, and one of the things I love about Desmos is it handles logs of different bases very, very nicely. Okay, to get a superscript or a subscript, hit shift underscore. So y equals 2 to the x, and y equals log base 2, log shift underscore 2, right arrow x. Okay, and I'm going to graph y equals x at the same time. Now I want to compare these to y equals 3 to the x. Okay, and I want you to look at what's going on to the red and the purple. They both go through 1 because anything to the 0 power is 1. But now we're tripling every time we move to the right. So we move to the right 1, we go up 3. We move to the right 1 more, and we go up to 3 squared, or 9. So it goes up steeper. Notice what's happening on the left, though. It's going up steeper, so it's going down faster, right? It's going down faster. So the exponential function is lower for the base 3 than the base 2 on the left. But the exponential function is higher for base 3 than base 2 on the right. And much is made of distinguishing between the two in the lesson. Now let's graph y equals log base 3 of x. Okay, and we're going to get much the same thing, right? The curve is tighter. It accelerates faster. And so on the left of 1, the log function is greater for the greater base and lesser for the lesser base. And greater than 1, to the right of 1, the greater base is less and the lesser base is greater. If you can keep that straight in your head. Okay? What I tend to remember is they both have the same intercepts, right? The x-intercept is the same for both logs. The y-intercept is the same for both exponential functions. It's just that when you increase the base, you increase the curvature. It's curving faster. It's accelerating faster. And if you remember that, it's easy to keep it straight if you can sketch a picture of what's going on. All right, so we are to identify and graph transformations of logarithmic functions. Haven't done that. Compare and contrast the logarithmic functions of containing different bases. We just did that. And we graph logarithmic functions. So we want to transform logarithmic functions. And all the standard transformations apply. So let's say I've got y equals log base 2 log. Actually, I'm going to do log, natural log. And log, natural log is log base e of x. And we're just going to modify that. E is the base 2.718282. Okay? And notice it still goes through at 1. It's a little steeper than log base 2, right? Y equals log base 2 x. It's a little steeper, right? The 2 it doesn't accelerate as fast. In fact, it's 2.7 is closer to 3, but it's a little less than 3. So if I said 3 accelerates a little bit faster or curves a little tighter. Okay? But what I'm wanting to focus on is what happens when we translate it. We can translate it up by adding. Okay? Let's do this. Y equals ln x plus 1 moves it up 1. Plus 2 moves it up 2. Come on. Fat finger. Plus 2, right? Plus 3. Okay? If plus a and add a slider, I can grab the slider and move it up and move it down. Right? That's just a translation up and down. Okay? If I want to move it right or left, I put a parenthesis around the x, and I can move it to the right by subtracting b. Right? Put a slider for b. As b moves right, it moves right. As b moves left, it moves left. Okay? And I can scale it. I can stretch it vertically by putting a C here, right? Got a slider for C. When C gets bigger, it stretches it vertically. When C gets smaller, it compresses it vertically. When C goes to 0, we have a little bit of an interesting occurrence here. And then when it goes negative, it flips upside down. So at negative, it flips upside down. Okay? And when I put a multiplier in front of the x, it flips it horizontally. Now what I like to do is put a parenthesis around the horizontal transformation and put the horizontal compression factor in front. Now remember, x is oppositesville. So if I put a slider in for d, when d gets bigger, it becomes more compressed. When d gets smaller, it becomes more stretched out. And when d flips negative, it flips it horizontally. Okay, and we can animate all of this. So all the transformations still apply to exponential functions. So if here are logarithmic functions. The main difference that you're going to recognize a logarithmic function when it has a vertical asymptote. Okay, when it has a horizontal asymptote, it's exponential. All right. Let me know if you need help.